Hi guys, so in this video we're going to talk about logistic regression. In this video we'll talk about its classical formulation, which is without a neural network. And then I'll talk about in the second video how it fits into neural networks. So remember from last time that we had a simple neural network called a perceptron, and its activation function looked like this. And basically, if it's less than 0, it's 0. If it's greater than 0, then it is 1. In most applications, you don't want this sharp of a cutoff for decision making, though. So, for example, if I'm here and I'm slightly negative, then I'll get 0. But if I were to slightly change the conditions of the input, then I have this drastic change, and I go completely opposite, because 1 and 0 are the only decisions I can make. We don't want that drastic of a decision to be that sensitive to the input that you give me. So instead, we can use a logistic function. And a logistic function looks like a perceptron, but it gives us more freedom on how sensitive we are to changes in the input. So this is its functional form, but qualitatively it's basically just a smoothed version of this. So if we look at this blue one here, and I were to draw this blue one down here and purple up here, we can see that it kind of looks like that one, but not exactly. You have more freedom. You don't have 100% certainty here. And we can play with the parameters of this. This A and B basically tell us an intercept and a slope. And, well, not an intercept, but where it's equal to 1/2. Or if it's equal to 1/2. It's not always equal to 1/2 at that center there. But if we make the B sharper, this value B bigger, it's going to be sharper and closer to a perceptron. If the value of B is small, it's going to be smoother. So in your head, the main concept you should take away is logistic activation function is an approximation to perceptron activation, but smoother, and we have more freedom. So in most applications, you're not going to see a perceptron type of activation function. You're going to see logistic or something else. Logistic is a pretty simple activation function. You might see something more complicated as you go forward. But so I'm just going to go through a simple example, and you can get this one on the Wikipedia article for logistic regression. It's the same data, the problem solved on there. I'm just going to talk through it. So for this problem, we're just going to look at the hours. We have 20 data points, and we're going to look at hours studied versus passing the test. So as you'd expect, studying more should make you have a higher probability of passing the test. And all we know is these observations. You know, the person either passed it or they didn't. And if you were to plot this as a function of hours studied versus pass, then that's what these data points would be, roughly speaking. If you want the exact points, you can go to Wikipedia article. And what logistic regression asks is the question: best A and B such that 1 plus e to the minus a plus bx fits the data. So, for example, here I have 3 curves drawn. Is it this one? Is it the gray one? Is it the blue one? Is it the green one? Is it none? And this is non-trivial. It looks on the eyeball that this blue one should fit it better because some people are still failing here. This green one is certainly not, shouldn't be correct. It's basically saying once you study 5 hours, you're going to pass, but these people, and you're not going to unless you study 5 hours, but these two guys passed. So the blue one intuitively should be the one that fits best, and you'll see at the end that it basically, the Wikipedia article, that one looks similar to the blue one I've just drawn. So the question is, how do we answer this fits the data question? And we formulate that through an error minimization. So we're going to find the best A and B such that this function gets minimized. And where we get this from, you don't need to worry about. So this is, if you're interested in the statistics, this is we're solving for maximum log likelihood. And so this is the negative of the log likelihood. So it's the same as minimizing the negative of the log likelihood. This PI term, this is the predicted probability of pass for ith student. And again, I goes from 1 down to 20, where the predicted probability is given parameters A and B. So in this case, this would be 1 over 1 plus e to the minus a plus b xi, where xi was the 0.25, 0.5, the hours studied. And so if you plug this into a computer program, this is not something you can solve easily by hand. You need a computer, basically. And you can check the Wikipedia article. Those values for A and B are negative 4.0778, and B is 1.047, roughly. These are approximate, because again, the computer can only approximate it too. And that's it. Now you have a model. And that model will look like this blue curve. And so this is your classic logistic regression. We'll show next time, we'll show the neural network, how you would formulate this as a neural network. It's basically the same thing, but then I'll show you how this fits into more complicated neural networks.